This is your physics introduction to the first law of thermodynamics. This equation should look familiar to us from when we did energy previously. We have gravitational potential energy, PEG. You have elastic potential energy, PES. We have kinetic energy, that's energy of motion, before and after. So before some change occurs on the left side of the equation and after the change occurs on the right side of the equation. We used this to determine all kinds of things when we did energy in a previous unit. There's another term on the left side of the equation, and that is the net work done, which can be positive or negative. Remember for work that if the force and the displacement are in the same direction, that's positive work. That's an increase in energy. If force and displacement are in the opposite directions, then that's negative work. That is a decrease in energy of the system. As you can see for this picture, the ball has increased its temperature. It's a color corresponding to a higher temperature, and that's because the boy did work on the ball when he bounced it. There was a force and a distance as the ball was stretched and compressed as it was being bounced, and it increased the temperature, increased the internal energy of the particles that make up the basketball, which increases its temperature. So this equation should be familiar from energy in a previous unit. What we're now going to do is add this other term, E internal. So capital E, INT is internal energy. The internal energy before a change and after a change. And again, that corresponds to the temperature. The temperature of a substance is a measure of the average kinetic energy of the particles, which we just call the internal energy, the energy of the individual particles. Again, we're not talking about the kinetic energy of the ball being thrown across the room. But as it is held in the boy's hand, the particles are moving, they are vibrating back and forth. If you increase the temperature by whatever means of the basketball, those particles are moving faster. So, because we're going to do a more classic thermodynamic example, we're not going to have the basketball or the cylinder of gas being thrown across the room. So we eliminate these terms. We eliminate the gravitational potential energy. We're going to say it's going to be sitting on the same table. Elastic potential energy, there's no rubber bands or springs. Kinetic energy, it's just going to be at rest on, counter or a table. So we can eliminate all those other terms, and this big long equation becomes much more simple. What you get is that the work done, the net work, is equal to the change in internal energy, final minus initial. We're always going to be referring to changes in internal energy. Work done, the net work, can be positive or negative. What we're going to define our terms, though, as that if work is done on the system, work done on the system, then that would correspond to an increase in internal energy. So if you have positive work done on the system, that will be an increase in internal energy. How can we measure that? How can we measure an increase in internal energy? Temperature. Temperature is a measure of the internal energy of the system. So here's our more classic example for thermodynamics, and that is going to be a gas enclosed in a cylinder with a movable piston. There is a way to get to transfer thermal energy in or to transfer thermal energy out. That's what the hot and cold reservoirs show. So starting with our equation for the work in is equal to the change in internal energy, we're going to talk about that a little more specifically. What if you go ahead and move that piston in? You push the piston in. Well, then that piston exerts a force on the gas. It is in the direction of down, according to this picture. So the direction of the force on the piston is down because the gas particle, where's that force coming from? The gas molecules are hitting the piston up, but the piston pushes on the gas particles down in an opposite direction. So the piston can only exert a force down for this orientation. What is the change in displacement? What is the displacement of the piston as it is exerting that force? Also down. So if you have a force down and a displacement down, that's a force and displacement in the same direction. That corresponds to positive work done. That corresponds to an increase in internal energy. And we have an equation for that. We say that the work done is F cosine theta. That's if there was an angle for the theta there. Delta x equals F delta x. We eliminate the cosine theta because there is no angle, it's an angle of 0 between the force and the displacement. They're both pointing in the same direction, which is down. but not very easy to measure forces if you are working with a sample of a gas. What's much easier to work with is pressure. We'll derive this equation in class together, but for now, know that we have a pressure times an area times a delta x, which then corresponds to delta v, and we'll explain where that negative sign comes from. But the short version is the work in is equal to negative sign, so like a -1 out front, times the pressure of the gas. That pressure must be positive, and delta V is the change in volume. So thinking through our options, if you push that piston in, then you would have a negative sign times a positive pressure times a negative delta V, because if you have pushed the piston in, you have decreased the volume, which is negative delta V. So a negative times a positive pressure times a negative delta V gives you a positive work done. What do we know happens when you do positive work? You increase the internal energy of the system, which corresponds to an increase in temperature. So these are the equations that you will use. Work in is equal to negative P delta V, which corresponds to the area under a curve for a pressure volume graph. So if you have a graph of pressure versus volume, the area under that curve corresponds to the work done. There's one other way that you can change the internal energy of a system. This is the one that's more obvious to us generally, and that's by transferring heat. So a change in thermal energy. So if you put a flame under this this piston full of gas, or you allow energy to flow from the hot reservoir, which is what that would sort of correspond to, then that would make sense that you would increase the temperature. That one usually makes more sense to people. Two ways to change the internal energy of a system. You can do work on that system, or you can add or remove heat from that system. So you can change internal energy, either increase it or decreasing it, by doing work on the gas or having the gas do work on the surroundings, or transferring heat in or out. That equation, delta E internal equals work in plus Q in, that is the first law of thermodynamics in equation form. Putting all this together, you get your whole list of equations. You have the ideal gas law. You have the ideal gas law in a before and after format, which basically derives all of the individual gas laws, Boyle's law, Charles' law, all of those. You have first law of thermodynamics in equation form. You have a way of calculating work from pressure and volume data, and knowing that the work done corresponds to the area under a graph of pressure volume. Our first example for constant volume, if we have an enclosed system, no gas enters or leaves, then we can cross N out from both sides of the equation because there's no moles. Remember, N stands for moles of gas. There's no moles. There's no change in the moles. They're trapped in there. They're staying in there. N is not going to be a factor. It's going to be the same on both sides of that equation. We also can eliminate V on both sides of that equation because this is the particular example of a constant volume. If volume is constant, then V would not appear. So this whole equation reduces to P1 over T1 equals P2 over T2. Remember, for these relationships, when you have a fraction equal to a fraction, generally easiest to solve those by cross-multiplying, and also critically important that those temperatures are in Kelvin. They must be in Kelvin to use as equations. So how do you accomplish this realistically? You'd lock that piston in place. So the piston was not free to move. To be another way of saying you have a rigid container. Energy could go in, energy could go out. You're not doing anything to prevent that from happening. First law of thermodynamics in equation form, delta E internal equals work in plus Q in. And we have our basic relationship there. But now, because we have no change in volume, this is the specific case of constant volume, delta V is 0. Therefore, work in is 0, Therefore, there's no way that you could change the internal energy of the system by doing work, because you can't do work, because you have a constant volume situation. If you have a graph for this, for constant volume, if you change the pressure, that's just going to go straight up from A to B. What do we know about the work? The work is the area under the graph for a pressure volume graph. There is no area under a vertical line. There is no area underneath a vertical line. If it was a horizontal line, there'd be area underneath. It's a vertical line, so there is no work done. That should match up. And if you did increase the pressure, then if the pressure did increase, you would have a higher temperature. Remember that temperature corresponds to the multiplication, the product of pressure and volume. So from situation A to situation B, that does indicate an increase in temperature because the product of pressure volume is greater at point B than it is at point A. Hopefully that's enough to get you started.